Evening, Al.
Hey guys.
I could go through my stuff again in a less personal manner if people want to hear this. So at Danfoss, we're trying to make products to put onto a tractor, something to sell to third-party, what do you call it, OEM manufacturers, so they can automate their vehicles. So we set up a demo, and we created a tractor. We made it drive from a ROS-based computer. I just had a picture here if I can find it again. And let's see, share my screen. So that's the, let's kind of zoom in a little bit. So that happens to be a John Deere 4044 tractor. And basically we put a Danfoss controller like this on it, which is a standard Danfoss product that is programmable. So you buy it and you hook it up to whatever you want on your vehicle. And that's what does all the low level controls. So we used one of these to control the transmission and to control the steering and read various sensors that were on the vehicle. So that gives you a low level drive by wire capability. And then we put a desktop computer on it running ROS, and that was sending commands down to this vehicle to make it move around. And you can't really see here, but underneath there's a laser scanner there, and there's a laser scanner up here on the forks. And then back behind there's a sonar that tells you how high this is, and there's a tilt sensor to tell you what angle that's at. And there's actually a radar on the back that it was an expensive radar, and now we're going to take that out and put a cheaper radar on there. And it's got this up here is a GPS antenna, a fancy blue flashing light I found at the local surplus store. So what they did, they put this together for a trade show, and people drove it around. They had the tractor in Denmark. Excuse me. I'm gonna have to pause here for a second. I'll try this again. So they had the
Are you using the Preco radar?
That's what the new one's going to be. The original was the Delphi, and it was like $5,000 or some ridiculous amount they wanted for it. And the Preco radar is like $500, so it's a tenth of the price. And I haven't really played with it a lot, so I don't know how well it's going to work, but that's what they want to put on so we don't back over anybody. And so we had this, we took it to a trade show, and the tractor was in Denmark, and the trade show was in Germany, and people would stand there at the, let's see if I get a picture of that. Let's see, how do I switch screens? Can you see the picture of the people standing in front of that?
You have to turn the screen sharing back on.
Oh yeah. Screen share. Okay, this is what they had set up in the booth in Germany. And this TV screen in the middle, in fact, the top 3 TV screens were live video of the tractor in Denmark. And then down here they had a like a tablet computer on a post sticking up, and you could go up to this thing and you could punch that and say, I want to pick up the box and move it over here. So they had it so that the tractor could actually drive up and pick up this big box that we made. So it'd use the laser scanners to find the tractor, or find the box, and it would drive up, use a sequencer, and it'd find the box, pick the box up, and then where you told it you want it to go, it would drive to that point and then set the box back down. And that ran for 6 days constantly, and everybody was pretty happy with it at that point. So then moving on, they decided they wanted to get rid of the ROS computer and go with something smaller, basically de-ROSify it. So they're going to rewrite the whatever modules we needed to make it run on things. And what they ended up doing was, this is one of the it's just like the other controller, but it being gray, it's not a safety controller. The safety one had the dual processor, and this one is just simply like an ARM Cortex-4 processor or something. It's exactly the same kind of thing where it's got pins that you wire up to your solenoids and your valves and your joysticks and everything. And they said, well, let's get the code to run on that. So what they want to do now is they want to put one of these on the tractor and take whatever code we had running in ROS, or like a subset of that, and make that drive the vehicle around. And in addition to that, so since Danfoss did everything with a CAN bus, this thing has a CAN bus interface to it, and that's all that it has. There's no other way to get data in and out of it. And since they do everything in CAN, they went out and they bought this. This is a LORD IMU, something brand new that's got a CAN interface on it. And unfortunately, well, it's got CAN, but unfortunately, it no longer has a magnetometer in it, so we can't get any yaw values out of it. We have no idea what direction we're pointed. So even though we found something with CAN, we lost the fact that we don't know what direction we're pointing. So another thing they did, here's one of the new Novatel Smart 7 receivers, and this one has a CAN interface on it. And again, it turns out the way our controller works, we can't take advantage of all the fancy CAN messages they put out, so we have to use the NEMA 2000 messages, which we can get latitude and longitude, and we can get speed and heading. And then there's another package packet that comes out that has a lot more information, like higher resolution latitude and longitude, and something that tells what kind of fix you have right now. But it's not quite what we need out of it, but we can't read the other messages. They have all these fancy binary messages that if our controller could decode those, it's got all kinds of good information we can use. So again, because we bought this CAN interface, we're trying to use it on our controller. We can't take advantage of all the fancy features. So basically they're going to take what?
That Novatel 7, does that one, it's a INS, so it gives you the heading and GPS, so you'll use that?
This one does not have the INS, and just like 2 weeks ago, somebody says, "Oh, we should get one of those for Jeff to take to Denmark," and I was looking at it thinking, well, so since we can't get the information out of this one, I can't imagine that that's going to give us the information over this format that they're giving us. And we had a conference, and they said, "Oh yeah, it'll probably work for you." But so anyway, I decided I'm going to take this one along. So at this point, you can get, in fact, let me pull that up since I'm sharing things here. So this is what I was doing today. I put the Novatel on top of my car, and I ran it. See, you ran it 3 times here, and over here when I first turn it on, it gives you a 0 saying there's no fix. And then shortly after, it switches to a 1 saying you have a single point fix. And then it switches to 2 saying your PPP is converging. And after some time, it says your PPP has converged. And if I had a different plot up here, I could show you. Basically what happens is when you first start it here, there's a big spike here, and it slowly moves down like this. And when it gets to this point right there, I think it's like within 1/3 of a meter. And it says, okay, you've got a good enough fix to start running. And it turns out that's configurable. So I can actually move that down to, say, 10 centimeters. Right now, they've got it set to 32 by default. So anyway, this comes on. And if you leave this running, it keeps converging down and getting better and better and better. So it gets out here. It gets as good or just about as good as RTK data, but it can take up to, say, half an hour for it to get that good. So it was taking like, I think I was looking at my plots here, it takes like 12 minutes from the time you turn it on till the time it's giving you something that's within 1/3 of a meter, and it's just going to get better from there. So when I turned that on, you can see how that was running. And then down here, this is the output of the heading and the velocity. So the blue is actually the heading, which comes out over NEMA 2000, that comes out in radians. So it actually goes from 0 up to 6. It's the numbers over here. So it goes from 0 to 6.28 radians over here. And we've got it multiplied by a fairly big number here. So, but anyway, that's supposed to be, that comes out to 6.28 radians right there. And then on the left, this is the velocity in meters per second. And that's, it puts out meters per second. And this is times 100. So, right here, you can see I was driving it where it says 500. That's actually moving at 5 meters per second, which is about 10 miles per hour. So if we come down here, this plot is the zoomed in of this first one here. So basically I sat out there until it locked on, and then I backed out of my parking spot and drove around. And you can see the orange here is the velocity, and the blue again is the heading as I drive around. And what that's doing, this is down here. So this is I was in this parking spot right here. Then I backed out of the spot and drove down here, came around the corner, and came all the way back to this parking spot. So if you look at this, you can see right here, this long spot at a constant speed of 10 miles an hour. That's this first path right here that I was driving on. And then when it comes to, then you can see I slowed down for the corner. And as I turned the corner, it started coming up and it rolls over because it tried to go greater than 6.28 and it wrapped back around to 0. So we were going at this heading, and now we're going to be going at this heading, and I accelerate back up. So that's down here.
Are those lat long posts out of RTKlib or charts that you have?
No, this is just Excel. What this actually is, I've got the CAN buses putting out NEMA 2000, which goes into our controller, and somebody wrote decode software here, so it's putting out actual, decimal numbers of latitude and longitude and velocities and all that. So this is simply dumped to a CSV file, and this is just Excel plotting those numbers out. So you just grab the columns and tell it to plot those. So anywhere it's a straight piece like this, that's on the chart down here. That's a long straight piece that's going around. Then there's a curve, which I think is this one right here, and then another straight spot. So then as I said back here, I ran it 3 times. So the second time I ran it, I started it up and I drove around the building once, and then drove around a second time. So you can see this part of it looks like this part of it here. If we go down and look at the plot here, oh, I'm totally lost now. Oh, there we go. So this one, I started my parking spot here and I backed out and drove around, came around here and went past the parking spot and went around a second time and came back and parked again. And you can see right here there's a slight divergence, and it's basically and most of that's because I couldn't see where I was going, down the road. Although there is snow on the ground here, so when I was coming in the back of the building here, I could see my tracks, and you can see those are right on top of each other as I was driving around. But as I go around the corner, they would kind of diverge a little bit, and when I first started here, it was diverging a little bit. But anyway, the receiver itself seems to do a really good job. I don't really care for their setup software, and I don't care for the sales guy, but in general, the receiver, once you get the receiver running, it seems to be doing a good job. I'd like to get more information out of it, but we're stuck with what we can get over that one single type of can packet. So that's what I did today. I played with that, and I was trying to see how long it's going to take for it to lock on, for when you, like this thing here, when you first turn it on, how long does it take till it's usable? And I say that's about 12 minutes. And then I've noticed before that once it gets to that point, like another 12 to 15 minutes, it gets down to the point where it's as good as RTK at that point, or it's real close to RTK. And then just as a test, after I drove it, I turned it off and ran it again. And it took a shorter time the second time to lock on and be good. And then when I ran it the third time, it's about the same as the second time that happened. So that's kind of where I'm at. That's what I did today, and I've got 2 more days to get this stuff running, so that's right where I need to be, I guess. So
That looks good. That's impressive. What do those Novatel 7s run?
Well, it's something else. They won't really tell us.
Okay.
It's one of those things. So we got it for free, and then we said, well, we want one of the ones with the IMU in it, and they said, well, here we'll give you a quote to buy one. They're going to sell it to us probably at list price, whatever their price is. I think the base unit was like $1,800, and then the IMU added enough that it came to about $5,000 for just the hardware. But you can't use it until you sign up for their. You have to subscribe to their services to get correction data, and you can't just get correction data. You have to sign up to get the PPP function to work. So you get all these little things. You got to keep putting money into it, and they won't tell us what that's going to cost either. So they just keep saying, "Oh, when we get all done, we'll sit down and we'll discuss this." And I keep complaining to him, and he doesn't care. So, and since I'm not making the decisions, I think we're going to go with it. No matter what I think. So. So as I say, they're going to sell us a unit for $5,000, but that's probably not what a customer would have to pay. They probably have to pay more than that. And then you have to get the correction service that comes off the satellites. So I'm not putting the core's correction data into this. This actually gets data right off the satellite. So you just turn it on, and as long as you got a clear view of the sky, it directly downloads the correction data and works. So you have to pay for that service, and I don't know what that's going to cost. But in order to use it, then you have to pay to turn on the PPP function, which I think is precise point positioning. I think is what that stands for, which is something new to me. And so there's two things you have to pay for there, and there might be some other things, licensing you have to sign up for before you actually get it to work.
That's excellent. I think on the Trimbles, it's like 2,500 for each one of those steps to turn on different features, or maybe it's $2,000 or something around there.
I don't know how long. Is that like probably yearly subscription? So every once a year you have to repay that. That would if I were trying to get money out of people, that's what I would do. I would say, because I know right now he gave us a 30-day trial subscription, and somewhere in they originally were going to give us the thing is they're going to give us a 6-month trial subscription on the TerraStar correction data. And that was great. I punched the code in, I tried to run it, and it kept saying, "Oh, your PPP has expired." So I got a hold of them. "Oh yeah, you got to pay for that one too." So now I think and they kept saying, since we're a developer, we can get these codes for free, but eventually, we're going to have to start coughing up money for this. So I don't know how that's going to work out, and I don't know, what they're going to have to pay for it. So, but if I compare this to the previous one we had, which was a Novotel. It was the SPAN IGN that had the fancy IMU built into it that we actually never got that to work. But we did pay, I think we paid $18,000 for that one. Yeah. And we bought it through a third-party reseller. So we didn't have to go through and haggle over all this stuff. They just said, here's a unit, you pay this, and it will work forever the way it is. At least I assume it will. We were just putting RTK correction data into it, and we weren't paying for anything extra above that. So since we never got that to work and the tractor disappeared into Denmark, we never played with it anymore. So it was a really fancy unit, but we never got it to actually do anything. I shouldn't say
it was pretty good.
I shouldn't say we didn't get it to do anything. The RTK worked just fine, and that's what we've been running on the whole time.
I used it for terrain compensation, and it did a very good job.
I guess that's all I have at the moment.
All right. Thanks, Jeff. That's interesting. Al, any updates?
Trying to find my mute button. Yeah, a little bit of progress. This, for folks who may not remember it, Matt and I have been working on the lawn tractor. It's basically a test platform. We have a little bit of a milestone list that we're working through. I think I'm sharing my screen, aren't I?
Yes, it's coming in.
Okay. So, Matt's all done and we're all trying to catch up with him, but
Matt's not all done.
So what I had been struggling with for quite some time is fabricating brackets for the steering motor. I'm happy to report that I got a draft set of those built and fabricated, and so that was significant progress for me. And then I've got a welding guy, a fabricator, coming over on Thursday to try to take what I've done in rough form and turn that into something more permanent. So a little bit of progress there. So then the next steps for me anyway is to get the angle sensor installed and get the transmission control actuator or servo installed. Matt had gone with the Super Servo 200, and I've got a couple of those as well, so I'll try to head down the same path that that he did. So inch by inch, making some progress. And hopefully, well, not hopefully, whenever I get the brackets more properly fabricated, I mean, I'm happy to share the photos and dimensions and all that kind of stuff, so it's hopefully easily transferable to somebody else who wants to follow our path. That's it.
Fantastic. You were looking at the low profile of the lawn tractor, and with that, I don't know if it's possible, but with that U-joint, can you bend that motor over so it's as low to the deck as possible? Or does it, I don't even know if it'll work like that. I'm not mechanical.
Yeah, my suspicion is you probably could. I was just starting off trying to keep the U-joint and the steering shaft in a line consistent with the original design to limit the friction and hopefully keep the amps down on the motor. Version 2 or version 3, we can bend it all in some convoluted shape. Because see, Danfoss, they had that nice sleek, I don't know what they made it out of. Got to keep up with the Samsons.
Yeah, that's made out of fiberglass, and I'm not going to tell you what they paid for that. I wasn't paying for it. And it's always in the way, I'll tell you that too.
Yeah, it is nice to have it looks clunky, but to have right down to the frame and everything open on the unit at the moment.
What is the model number of those garden tractors you guys have? What do they call that?
Hold on a second, I'll tell you exactly what that is.
The XT1 series.
Yeah, XT1, 42-inch, 18 horsepower Cub Cadet. In this spreadsheet that I shared, I'll turn it back on here, which is in the lawn tractor folder in G Drive if anybody's interested and doesn't have access. Not only do we have the task list that we're working through, but we've also tried to capture the bills of material that different people are working from. So there's the manufacturer and description. There's probably a more precise SKU, but it's the XT1 42-inch.
They do make two models. They make a fuel injected model and then they make a carburetor model.
Yeah, and daggone
we're gonna learn how to do both.
Yeah, so I got mine, I don't know, the day after Matt, and I think the models changed, so I've got the fuel injected model. So that'll be yet another learning. And I'm sure Sam will have great optimism in our ability to learn that.
I do. Absolutely, yeah. This things are coming along. I'm happy to see it.
Oh, and just by the by, in case anybody is wondering, the U-joint, let me try to get down to it here. This U-joint that connects the original manufacturer steering rod to the electric power steering motor is a very specific U-joint. Comes from these E-Power steering guys. I was able to drill that. I mean, just going slow with a 1/8 inch drill bit, so I didn't actually have to weld the steering shaft to the U-joint to join it up. So it'll take basically a number four bolt, which will be a stress point, right? So if it were to hit something and really jam things up, that little number 4 bolt would shear, hopefully, and offer some protection. So that's where we're at.
Speaking of your pin shearing off, that's a good reason to put a potentiometer on top of the motor and then put the one down on the bottom. And that way, if the pin breaks off, you'll see that your two position sensors won't match anymore. So that way, as it's driving around, if it breaks that, it'll know enough to stop.
So to have 2 potentiometers, one at the gear and one on top of the motor, is that what you're thinking?
Yes.
Yeah, I mean, they're not very expensive. It's just a few more brackets. Getting all this learning on brackets. We need a mechanical engineer on the team, guys.
Round one up.
Thinking about the U-joint, is it not that you need like a 2 at the end because it does not provide like the constant velocity at some angle, right? So does that matter?
Matt, I don't understand the question. Do you understand the question?
Not totally.
No. Like the U-joints, usually they use it in the pair just because if you need the constant velocity, like at 40 points, you have to use it into the pair so that it just actually, if you use one, then you would not get the constant velocity. I mean, it basically operates at an angle, right? So you don't, I mean, is it something's required or? I guess not, because I think probably if you're using the steering, rack and pinion steering, I think there where you got like 2 U-joint where you need the constant velocity. So I think in this case, just if it's just driving the one like a shaft in a gear, I don't think that you might need it. I'm just thinking.
Yeah, this is the actual website, and
Right.
so you do have a left and a right side to the U-joint. And I mean,
Right. So it like on the one side, let's say you have the steering, and then over there you just have the one U-joint, but you might need also at the other end, just make sure that you have the constant velocity transmitted. I'm just thinking out loud here. I mean, it might not be needed, but I've seen that used like in pair.
Yeah, we may find that out the hard way.
No, I'm just because I've seen that, and most of the time I see that it's used in the pair, and that's why I'm just questioning. I'm no idea. You might not need it, but it's something that I saw and I said might be useful.
Mm-hmm.
Yeah.
I think in this case, it moves slow enough. Moves slow enough. I don't think it's going to be an issue one way or the other. And also, since their steering sensor is right on the steering and not on the motor, I don't think you'll see anything from that.
Cool.
Which might.
Sam, any updates this week?
Yeah, I'm like the PR Pursuit implementation, like on the path, the tracking side. And then this is what I was just trying to do it directly into the Python just to see that how good, it actually tracks and follows the things, To my surprise, like just very pure implementation of the PR Pursuit, even without any like, tricks and inputting parameters and fine tuning. It just works perfectly fine. I mean, I'm just baffled, like how good it can track actually. So I was trying, and it was just one of the Python robotics algorithm that I was just trying to see that, how it tracks. And basically I was trying to see how my path is kind of generated. Like I'm just using the simple NumPy arrays to do my X and Y. Right now I'm not doing anything straight, but it's just like some kind of sine curve. Mostly is like through the function. And dividing those points, so I got the path ready. I'm trying to follow that with the almost constant velocity. And then the look ahead frame, which is what I call the CAD frame. I just wanted to see that how that moves, and how my vehicle like tracks that at this point, which is like just the dot at this point. I haven't, added anything sort of like a steering angle or the Ackerman style of steering. Just wanted to see that how it follows. It does the perfect job. I mean, I'm really happy with that. I think if this thing materializes, I think it would give us the really nice results, because I'm just using one of the proportional gain, just 1 kp use of it actually gives a really nice simulation. Now, the real life scenario is different, obviously. I just wanted to share that quickly. See if I can. So I'm not sure. I have to share the other screen because it pops up into the Matplot. So let me see if I can share this. And if I have to share the other screen, I can do that. So it's a very simple Python implementation. And as you can see that I'm not even using many libraries over here. It's just mains the NumPy. I got like math, which I'm using it for sine, which I could have used the NumPy, and then I'm just plotting it at this point. And then some, the variables that I'm looking at over here is just the look ahead distance is what I'm using is 1.0 right now. And then my, the delta t is sort of 0.1. Using 2.9, which I'm just, kind of taking it from the program, but I'm really not using that at this point. Basically, if it relates to our ROS terms, the state is what the rigid body state, and that's pretty common. What you can describe like a state. State's something like your position and your twist data. So basically your location, kind of XYZ, your orientation, and then you have a twist data, which is your linear and angular velocity. So this is what we're defining, and then that's the only the class object that we're defining over here. Other than that, everything else is like you were just actually calculating your target next index based on your array, and then you're implementing passing your state, the array of CX, CY, and your next, the index point basically. Other than that, everything is like the simple calculation of the curvature and the angle. What's the the look ahead angle, and basically how you approach that. And for that, from get to the point 1 to the point 2, depending on the curvature and the angle, you just decide that if you wanted to slow down a little bit, or you can just go at the full speed. Not a big deal. So over here, for example, I'm just using this simple, the array for the NumPy to define my X and Y. So this is basically my coordinate points over here. I am actually doing 1.1 divided by 3.6, which is like converting your kilometers per hour into the meter per second. So using like about, the either 1 kilometer an hour or like about 10 kilometers an hour sort of thing. My simulation time is just for the simulation purposes. And then I'm just keeping an eye on the last index just because I wanted to stop, before I hit my last, the XY, basically the point. I kind of initialize that and then, give it to the state and I get the values. Once I get the values, I just define the array for those like as a list. And then we just simply run it, through the while loop, and while my last index is like greater than my target index, which is like almost the last array minus 1 point kind of a deal. If I run this, just beautiful tracking that, I was really amazed. So let's see if it should run. Okay, can you guys see the screen or no?
It opens a new window.
Okay, so
We see Python code.
okay, so let me share this window now. And you should be able to see that. See, simulation started already. And then this is the green that you can see is my function path, like my array. The red, as you can see, it is moving. It's my, the look ahead distance, which is my target frame, which is like, I call it a cat frame. And really the blue line, with that dot, it's actually what chasing it's your vehicle, and that's localized right now. So with the with the like 1 forward gain, see over here, as you can see, just a little bit of PID gain where it just drifted a little bit. But other than that, it's just simply following, the points really well. If I ROSify this, this is my vehicle frame, and this is my actually the look ahead frame. So those two frames that I can add basically, and then that would, for example, if you have see that grid, if I have the perfect, the path planned, and if I provide that, imagine that your tractor would not sway, and even if it sways just for any reason, let's say it spoofs or what it just goes off track, it will try and gain, and then come back online. I mean, provided that your field is not really at has no like certain ascent or descent, like not crazy ascent or not crazy descent. I think it would just work fine. That's what I think at this point. I mean, based on what I see, actually.
That's pretty cool, Sam.
Sam, I'll further. That's really cool. I spent time trying to figure out Pure Pursuit, and I think I have it working in DIY drones, but I never ROSified it, and it ended up creating this pseudocode. It's in the Slack channel. Again, I don't know how much time you have, but it would be great to sit down and compare notes on how you did it and how I was thinking it was going to work, and did it in another language.
Exactly the same. Like this is the Pure Pursuit. I can see that your rabbit is your look ahead, and where you're located, your tractor is your current point, and if you're like, what you're doing right now is your waypoint A and your waypoint B. So your tractor would move, your green dot would move to the closest point, which is nothing but the algorithm where you have a dot, which is your tractor localized versus your straight line. So you wanted to get to that point first. So you go there, like closest path, basically from point to a line, which is like a simple formula that I have used it in my program. So when it starts, it just goes there first, and that's the closest point. And then from there, you have this rabbit, the look ahead. So that exactly your look ahead distance where you constantly keep looking on that path. Right. So that point that you start chasing and your tractor is now following that path. Now, the only problem with that, if you have the any angle or the curve where you have to figure out the alpha, which is like the angle between your next look ahead versus where you're at. And then what you do is you try and get that, because now you have to steer, so you use the PID to get there, because you don't want to accelerate, or maybe sudden deceleration is not good. So you wanted to use that, the KP, just maybe you can just use the whole PID. I haven't done that, but I have just used the KP because that was also available into the program. So with just KP, I think it actually stayed on course. And for most part, my optimism is where that if we are able to figure out almost a straight line and then only the headland where we have to turn, that's where we have the circles are, I think pure pursuit should work just fine. That's where my optimism is. Because
Yeah, the guys over in Ag Open GPS, they use Pure Pursuit. I mean, I think they have a slightly modified
Yeah.
Pure Pursuit. It's written in C#,
Yeah.
and not necessarily Rossified. So, I mean, you've got an approach. I had an approach. The Ag Open GPS guys have, an open source. One thing to think about, and I've mentioned this to Matt a number of times, is, if this is waypoint A and this is waypoint B, and the tractor finds itself here and it's got to get back to the rabbit,
Yeah.
and this what is commonly called the cross-track error.
Mm-hmm.
Keeping track of that cross-track error, think about how you would keep track of that. It's a very simple thing, but at the end of the day, in my mind, what we're looking for is a steering module that produces the least amount of cross-track error.
Correct. Yeah, once it's on the path, once your starting point, and once you're on the path, you just want it to stay course, and then you don't want the cross-track errors. You want it to minimize that as much as you can, right?
And I got to the point in Ardu Pilot, I'm never quite sure if I'm pronouncing that right, and using Python and Pure Pursuit in Python to drive. They had software in the loop simulation tools in Ardu Pilot, so I could actually simulate this before I abandoned Ardu Pilot. But yeah, hey, I'm hoping to be in Texas in a week or so, and Matt's going to come over and we're going to run an A/B test, and we'll try in a real field see what our cross-track error is going to be.
Yeah. Yeah, I think the whole thing would be depending on how good the localization we can get to the point where how localized we can get our tractor into a map frame, because I think the Pure Pursuit, like after that, once we localize our tractor, and it's a pretty good localization, in a way, applying the Pure Pursuit should work just fine. That's what I'm thinking.
Great for the Ag Open GPS guys. I mean, they're they really are happy with their setup based on their forum comments.
Because when I see the straight lines, like where it has to follow, I mean, it has no angles whatsoever. I mean, there's a little slight variations, but not crazy variations. Like what I've just showed it to you, it's like complete similar to the sine curve. And if it can follow that, with that precision, the straight lines are, like I said, I'm more, that's where my optimism is. Like it should follow just fine. And in headland, you don't really care, just because that, if you have the right path, it would turn. And then I think we can actually make it a little bit adaptive so that it will go to the maximum velocity. We don't have to keep the constant velocity if you can. At the turns, you can actually slow down, really, and it's not a big deal, just by looking at the turn and the curve. You just slow down, you just take a nice, decent, the turn, and then you just go back to the path, and then just keep going on to the max velocity that you specify.
Right.
So,
I mean, if the test, and again, just to think about is the Ag Open GPS guys, they don't use odometry, right? I mean, a test would be just to take a straight non-ROS Python simple one point A, 1 point B, and run a 300-yard test and see how it does. That's what I would hope to do.
I'm assuming that code, if it's just pure Python, it's not much different than what we have just seen,
Mine is Python, but again, the platform was going to be Ardu or Ardu Pilot. The Ag Open GPS guys are C#.
Oh, they're C#. Okay.
That's good.
But, I mean, certainly the structure, it's likely you can reverse engineer it.
Absolutely, yeah. Yeah, this is the same thing actually. It's just no different.
So we're running up on time, but Kalyan has a project he wanted to go over tonight.
Sure, perfect.
I don't know if you have your show and tell set up.
Yeah, I got my project set up. Let me see.
And the share screen is on the bottom of the Zoom window. Kalyan's an expert in deep learning, and he's been working on a project to identify plants and weeds. So kind of an interesting project.
Can you see my screen?
Yep, we can see it.
Is there an echo? Okay, so I actually was in the Ross Ag team a year ago when the group was started. So I have to say, when I come back after 6-7 months, I'm just scared with the knowledge you guys have. So just amazing how much progress you guys have made in last 1 year. So very excited to see all the stuff which is going on in the community and all the projects. So looking forward to be back again on track and work with you guys. So what I've been working on is mostly on deep learning algorithms. The state of the art in the deep learning algorithms has been moving so fast, it's hard to keep up with, with it actually. So it's like a full-time job for part-timers. So it's pretty interesting. And I've been working on a couple of computer vision projects lately. One of the idea for me lately has been to do a project in AgSpace. And with all the learnings we have done in other domain, I want to see what we can do in the AgSpace. Now, the challenge with any of these deep learning projects are three. First one is finding the data set and finding cheap hardware to do all your computation. And the third one is training time. So when I started a year ago, finding data set was pretty hard. Now it's getting to a point where many people are willing to share the data sets, and there's a good platform in many cloud spaces to share the data. As far as the hardware, what was interesting to me is, in the past, if I had to use cloud for computation, it was breaking my bank. So I had to spend like $100 or $150 every month to do all the computations for deep learning. And then the training time was ginormous. Like I was spending an hour in each training set. So how many of you are like, I guess most of you, I'm assuming, have seen deep learning in some form or fact, right? Now, what I started working was working on a Kaggle competition. So Kaggle is a competition where a lot of people put their data set, and whoever wins the competition, they give a prize to them, $10,000 or $20,000. Regardless of the money, it's still fun to participate in the competition because you get to learn from other people how they're doing deep learning and get to learn some of the state-of-the-art techniques from them. And at the end of the project, they actually list where you are in the competition. So for this one, I think I'm in the top 100, but it took a while to learn like how to get into the top hundreds or top 20s. So what I wanted to share today was a project I've been working on for deep learning. So the idea here is you'll get all the data for this data set from here. And I don't know if you can see the image. Can everybody see the image? Oh, perfect. So inside the data, they provide the data here, and they give a training set and test set, and they classify different kinds of plant seedlings here. And the goal was to do a great job on test data and see if, what kind of accuracy we can get out of it. So for this project, I was able to get like 98% accuracy. The starting point when I started, it was around 85%, but then it went to 98% through some optimizations and techniques I've learned along the way. So I'll share some of them here. But at least the goal was to for the community to share some of these, and we can probably work on similar challenges or similar data sets afterwards.
When you say 98%, that's super cool.
Yeah, it took a while. So it took a while, a lot of copying, hacking from many places, but it's yeah, once it's all done, it's pretty interesting. It's actually addictive at the end of the day. You get so addicted to improve the accuracy every day. So my wife keeps seeing all these plots and like, what are you working on? Where do you keep this stuff? So I got to be careful about this addiction. But then again, like I also know that, you know, you can only go faster if you're doing alone, but you know, if you can go farther if you are together as a team, right? So that's why I want to share this with the team, and then probably look forward to learning from you guys also to enhance my knowledge, and then share whatever I learned along the way. So I'll go very high level here, but then again, we can, if anybody's interested, I'm definitely happy to hear from you guys, and we can take some of those offline as like about the details of any of the code. I also wrote a Medium blog. So I wrote a blog here, so I plan to share this on the community also, as what are all the steps I did along the way and what each piece of code does. Just to get my thoughts on some place. And while I was writing, I also noticed all the blind spots I had, and it made me realize, oh my God, I don't understand this completely. So I need to go back and understand this because I took a lot of code from many places and hacked them. So it was an interesting experience to write a blog. So going back to the project, you can see that you know, I'm using Python code here, and I'm using Jupyter here to do most of my training. And then once I'm done with the training, the idea is to take the model and then classify the images into different types of plant set. Matt mentioned that it would be nice if we could take one of these prediction algorithms, put that into a Movidius stick, and see if we could use this in real time. So I think those are some good ideas we want to pursue in next couple of months, and then augment with the big vehicle you guys are building. So we could probably help out on the perception side. So most of my concepts are taken from a course which is which is called Fast AI. It's a very practitioner learning course. And I'll post a link to that one, but it's a very good course. It will speed and accelerate everybody's learning on deep learning. So I definitely highly recommend that course. So those are the libraries I'm loading from. And then here I'm loading this data set from Kaggle. And then once you get the data set here, I have to do some cleaning to make sure that I get the data into the right folders and format. Once I get the data into my cloud, so all this is running in my cloud machine here. And then I copy all those, and everything stays there on my Google Drive. So once I get all my data, I do it once, but after that, it's pretty easy from there. And if you guys have known, I don't know how many of you guys have known this, but Google has introduced something called Google Colab. The neat thing about it is they give you a GPU for free to do all your training. The idea was to use their platform but I found a website called Cloudriser, which allows you to use Jupyter Notebook, but at the same time use Google Colab to do all your training for free. So I've done like $200, 200 hours for now of training for $5. In the past, 200 hours would have taken me like 100 or $150. So this is pretty cool that now anybody can start using it in a very affordable fashion. So once I got the data, I'm looking at the data set here to see how distributed is my data. So I got wheat, charlock, sugar beet, all these plant seeds, and each one of them have 500 files. So for example, this one has 500 files, this one has 200 files, and then this one has 200 files, right? So the reason you want to look at this data set, the amount of files you have in each category, is because if there is one file set which is dominating, let's say this loose silky one has 1,000 and rest of them has 100, what deep learning will do is like it by default it will go and predict that as loose silky because it says it's a small error for it and then it's easier for it to train. So the idea would be to look at the data set distribution of it and make sure that it's uniform in its distribution. And if the data is non-uniform, so you would use augmentation to increase the data size. So if it's a time series, you would add noise to it and then increase your data set. If it's an image data set here, the idea would be to crop the images or rotate the images or flip the images and add like a virtual data set to it. In this case, I kind of left it alone. That's something I want to try, the data augmentation, so that this distribution looks uniform. So once I looked at the initial data set, the next step is to prime the data set a little bit, and then from there, start the deep learning. So here, the way I'm priming the data set is you can also do some augmentation online. So I'm telling what kind of transformations I want to do, but then I'm saying, if I have 1,000 images, use 800 images for training the data set, and then 200 images to validate your data set. So I mentioned the percentage of validation, percentage of the data set which should be used for validation. Another cool thing with the latest modern architectures is that in the past, if all your images were not of same size, you would have to do resizing before you feed it to neural network. The new architectures, they automatically can adjust to the image size. So pretty cool in the sense I didn't have to do any resizing here. All I had to do was do augmentation, which was rotation and flipping up the data. So once it is done, so this is all for exploratory analysis. I'm trying to see how many samples are there in the training set, how much data you have in the validation set. Now, another idea you want to always do is you want to normalize your data. So the images usually are from 0 to 255. Most of the deep learning ones, they want the data to be between -1 and 1 or 0 to 1. So this was one of the normalization step here. So I take the data and normalize it. In general, it's a good practice to look at the data just to make sure that everything is loading up properly and you got the right labels for your plants. So I use a tile here to look at my data.
Look at that wheat plant in the lower right-hand corner. It's amazing that deep learning can classify that as common wheat in the lower right-hand corner there. It's just like a little leaf.
This one?
The common wheat, yeah.
Oh, common wheat, yeah.
That's a wheat plant. It knows.
Yep, it's hard to see, right? But this one we haven't done the training yet. This is somebody who has labeled it. I'm just looking at the data to see what it looks like. Yeah, at some point it probably, that's a good idea. Maybe I should like classify that at some point and show a similar tile. So then usually the competitions will tell you what type of metric they want to use. In this case, they were using an F1 score, so I had to write some code to define what F1 score is. But once you do it, then actually the fun part starts. So you start to see that you spend like 25 to 30% of your time in actually cleaning up the data and getting it ready. And then once it is done, then we get to the actual code, right? So here I'm using a model which is called ResNet 101. This ResNet has been used on images dataset, which is called ImageNet. And this one was a winner in a competition last year. So this model was a winner in a competition last year. So what I'm doing is I'm taking their data set, their model, and then we don't, so now in the past, if you had like 200 layers, we would train all the 200 layers, and that would take 2 or 3 hours. What I'm doing now is I'm freezing all the 199 layers. So all those weights will remain constant. And then we add one layer very specific to this data set and train only the last layer. And when you do that, what you gain is you get all the knowledge from that architecture at very low level, but then you can apply very easily to your data set and get the power of it. So the idea here is we do something called transfer learning, where, like I was saying, you would freeze all the layers and do it only on the final layer. And when I do this, you can notice that the total time for me to run 10 iterations here took me like 17 minutes. In the past, if I were to do it without transfer learning, this would have taken me, good Lord, like 3 or 4 hours. So each hour I'm giving the Amazon cloud guys at $10 or $20. So, you know, it was a lot of money in that sense, right? So the main takeaway is always use transfer learning. But then one of the good practice you also want to do is once you trained your model, even through transfer learning, you want to save your model as soon as it's done. So we just save all the data into like a pickle model because it's very efficient in terms of data saving. Once it is done, we typically like to look at the data now. This is what you were talking about, Matt. So what we like to do is we like to run that on a test data set, which is the data set which it has not been trained on, and see what kind of errors you have. So for example, in this case, it was a Lucy silk bend, but the model classified it into small flowered cranesbill. So you like to look at what kind of errors the model has been doing and then start tuning that a little bit. And then in this case, what I found is like whenever I have a black grass, it tends to classify that into loose silky bend. In this case, it made the mistake 19 times out of 1,000 data set. So the idea would be to understand where is it making mistakes so that we can tune it again. So in this case, we started tuning it again. So I think the first time we got around, let's say 94% accuracy. So we want to see if we can do better than that, right? And then the final model after tuning, we got to like 98% here. And what's amazing to me is like, I have like no knowledge about domain knowledge about some of these plants, but still you could use deep learning to do very good classification, right? One of the technique I've been playing with is what kind of right learning rate you want to use for this. And playing with learning rate, you can find that it actually, in this case, all I did was play with the learning rate. They took from like 94 to 98% accuracy. And the other neat thing about learning rate is like most of the people, if you're solving a gradient descent problem, you would use a constant learning rate. In this case, we were using a differential learning rate, which means each layer would have a different learning rate. So the ones which are at the beginning of the neural network, they're not tuned that much, but the ones which are at the later stages of the deep learning network are tuned more because that's closer to your domain data set. So once it is done, all you do is like save your data set, save your model, and then pretty much you're done. So what I do after that is you come here, and if you have a folder full of images, we can take all those images and pretty much do say learn.predict, and then it will start predicting the right class. Usually we save all those to like a CSV file. for the test data, and then we would go back. Sorry, we would go back to this web page, and then you upload your submission here, and that's where I think my score was around 0.98, and then if we go back to the competition, 0.98 was around like 100. For some reason, I can't get back to the leaderboard. Oh, jump to your position on the leaderboard. So yeah, so if you see the competition, if you get around 98, we are in the top.
You're not sharing, right? So
Oh, I'm not. Oh, I don't know what happened. Let me see. I still see you guys, but okay, let me see.
Looking for the green box with the arrow coming out of it.
Oh, okay. Where did I lose you guys? Okay, maybe here.
We
There
see
it
the
shows
leaderboard now.
Leaderboard. Okay, perfect. So I think our score was around 0.9811. So we are pretty much in this, like, very close to like the 100th in the competition. With some more tuning and some more knowledge sharing, we can probably get into top 50 or top 20 of the competition. But you can see so you can see how we can apply knowledge from some of these courses and get into like and start solving some of these problems. So my thought was, I've been talking to Matt about this, and if there's enough interest on this, we can start a smaller subgroup on computer vision challenges and specifically on perception problems, and see what kind of problems you guys might have in terms of computer vision, and then we can come up with a neural network and also a way to put that into ROS platform using Movidia Stick or Raspberry Pi, and enable the larger team further. So to me, like I said, this has been very fun in terms of tuning and playing with this. And I said, I'm very addicted to this. So now I'm looking for more problems and more challenges. And I was like, we got plenty of challenges. We got plenty of problems. So we can probably feed the beast here and see where we can go on this.
This is fantastic. And I love the idea. The only thing I need from you from this, the thing is just your training data set, and I'm all set to go, right?
So yeah, I think you would. So the idea would be like when we're done with the tuning, we would just give the model, and then you would interface with the camera, and then pretty much done.
Yeah, no, this is fantastic. This is good. It's good to see that. I think, and then
Yeah, I echo.
yeah.
I echo
Yeah, but
Sam's.
basically, where are you heading to? What's your objective?
What is it?
What's your objective at the end of the day?
Oh, what is my objective at the end of the day?
Yeah, apart from getting the model to learn the difference between weeds and plants, how are you going to use this software? What do you intend to use the software to do?
So yeah, so maybe I wasn't clear. So the idea would be once we train this model, right? So let's say if you want to classify between weed and non-weed, and you might be getting images from camera, the idea would be to take this model, train the model in such a way that you could put that on the real vehicle and then classify plant as a weed or not weed. There might be other types of problems, so people might be interested. And I think Matt forwarded one data set where you want to find the row of the crop in a field so that you don't have your tractor does not go on the plant row.
So Colin, the application with identifying the weed versus plant is spot spraying. So you don't have to spray chemicals all across your field. It's only when you identify a weed, then you just spray that weed as you're going through.
Yeah, that's what I wanted to hear from you, because that's the farmer's problem.
Yeah.
You want to be the weeds. After all the excitement and they've gone through this rigorous process of coming to the end with a software that identifies plant, then what? But if you are going to end up putting it on some platform where it then sprays the weeds as it identifies it's separate from the plant, then the farmer is now happy. The problem is solved. And I think this is very, very interesting. Unfortunately, I cannot jump onto it. I've started something that is bigger than, but this is very encouraging. Thank you very much.
So kind of the idea that Colin is to kind of have smaller teams. So if a group of people are interested in the perception part, they can build this system to identify the weeds. And then another team, like Al's leading, is building the platform, getting the vehicle moving. But all of that integrates together.
Yeah, that makes sense.
Colin, I put the URL in the chat channel. You may have heard about it a year or so ago. John Deere spent $305 million to buy a company out in California that they take it one step further. Right there, as Matt said, they are applying herbicide based on the identification of the plant. The business case is incredible. It's like 1/10 of the chemicals and all that kind of stuff. And I often wondered what the story was about the extra $5 million that they paid instead of it not being even $300 million. But anyway, they dropped some serious money to buy the technology.
Yes, man. You said you posted that URL.
It's in the chat.
Did you post? Okay.
Yeah, it is. Now, just to make sure, like the one we got is just classifying the weed versus non-weed. In a real scenario, we still have to find the location of the weed in the image, right? And then we can classify whether it's a weed or not. So we only did object classification. We still have to go to object detection and object tracking. So there are many more problems.
Details. You have all that worked out by Easter.
There is a ROS package for weed for plant. It's called semantic segmentation, which basically looks at an image and then takes out the different shapes. And so with that package, that will tell us the location within the image of where that object is. And then once we can classify that image, then we know whether that's the plant or the weed. It's still a lot of work, but it's kind of a fun area to work in now.
Beyond plant classification, if you want to think about other use cases, I mean, there's probably better ones, but identifying fences and not crashing through fences, identifying hay bales and being able to, ultimately pick up hay bales and move them where you want to. I mean, Jeff talked earlier about, in that trade show, they could say, go pick up that box. I mean, it's the same sort of concept. There's lots of images that need to be picked up in an agricultural setting.
Kellyanne, thank you for the presentation. That's really interesting. We are a little long here tonight, but thanks for sticking in there. And we'll hear more about this project and see if we can get some people interested in another group. You guys have a great week, and we will see you on the Slack channel next week.
Thanks, Matt.
Thanks, guys.
Good night.
None.
Thanks, guys.